Okay, it's Brian here, and this week we're going to talk about one-dimensional motion, but I want to start by focusing on problem-solving strategies. Now here's something to be aware of. Let's think about the progress of the course. So this is the week when you hand in homework number 1. And as you're working on homework number 1, you can go to problem sessions, and we've got them on Monday, we've got them on Tuesday, we've got them on Wednesday, we have them on Thursday. So drop by the problem sessions either virtually or online. Work with me, work with the learning assistants to enhance your problem-solving strategies. And we're going to start by solving problems of motion in one dimension. And the reason why we start with motion in one dimension is that it's easy to wrap your mind around what's happening. And so this is the time to build good habits. You want to build good problem-solving habits. And I'll tell you something you want to avoid. What you want to do is you just want to go in and write down a list of everything you know, and write down a list of everything you want to know, and then say, oh, I just need an equation that takes me from what I know to what I want to know. Do not do this. Down that road lies madness. If you do that, you are short-circuiting the process. You're not really learning how to solve problems. You're just learning how to equation hunt. And we want you to learn how to do physics, how to think physics, how to solve problems in a substantive way. And so we're going to be looking at your strategies as you go, okay? And so when we're assessing your homework, we're going to be looking at what you do, not just your answers. And so when you're solving a problem, start with a story, draw some sort of a picture, and finally do your equations. And I can't stress this enough. This is the time in the course to develop good problem-solving habits, because one-dimensional motion problems, it's pretty easy to wrap your mind around what's happening. When we get to later parts of the course, it's much trickier. And so by the time we get there, you want to have really honed your problem-solving skills. Now in the textbook, every example that we solve uses this 4-step problem-solving strategy. Strategize, prepare, solve, and assess. And you'll see that. If you want to see examples of problems like that, go ahead and look at any example in the textbook, and you will see the strategize, the prepare, the solve, and the assess steps, and think about what we're doing for each one of those steps. And we want you on the homework assignments to go through those 4 steps. Every problem that you solve, you should be following those different steps, because you're training yourself in good techniques of problem solving, and that will serve you well later. Now here's what the steps mean. The strategize step is basically what's the big picture. How are we going to take this problem? How are we going to model it? What type of physics is involved? The preparation step is basically putting the pieces together. Okay, we're going to take that problem and we're going to break it into parts, decide where it begins, where it ends, record known information, decide what type of motion we have for different parts of the motion, and finally think about what equations you can use. And then you get to the solution step. Well, the solution step, if you've done all this work, is fairly straightforward. You're just taking numbers and you're putting numbers into equations. And that's fairly straightforward. You can train a computer to do that. Finally, and this is really crucial, you want to take a look at your answer and see, does it make sense? And that will help you figure out if you've kind of like taken a wrong turn someplace. But it also just helps you put everything in context. So always finish with this. This is crucial piece of the puzzle. So let's take a look at a sample problem. And this one has to do with zebras. And it turns out if there's a stationary zebra and it spots a predator, it will accelerate at 4 meters per second squared until it reaches a constant speed of about 11 meters per second. And this is actually real data from a research paper, okay? And so everything that we are going to do in this class is based on real data where possible from research papers, peer-reviewed papers, where these are real numbers about the way the world works. That's where the information comes from. And that will help you, because when you solve a problem, it's going to teach you something about the world, but you'll also be able to assess your results when you're done and see, do they make sense in terms of the real world? And it turns out there's a lot of people who study predator-prey dynamics. And it turns out predator and prey typically have different strategies for running. For instance, lions chase zebras. Lions are all about a quick burst of speed. They're going to go from 0 to a high speed very, very quickly, but their endurance is minimal. Zebras and other prey animals tend to have a lower acceleration, but they have a higher top speed, and they have great endurance. And so they can keep up that top speed for a long time. And there's been a lot of people who have studied this in some detail. Now I want to note here, this top speed that you see, 11 meters per second, that's about 25 miles per hour. That's speedy, but zebras can certainly run faster than that. But in the wild, they don't run faster than that, because if you're being pursued by a lion, the last thing you want to do is make a mistake. And if you're running at less than your top speed, you're less apt to make a mistake. And it turns out lions run at less than their top speed as well for exactly the same reason. Mistakes could be fatal under these circumstances. Anyway, given that data, here's the two questions that are asked. First off, how much time does it take for the zebra to achieve its top speed? And two, how much distance does the zebra cover as it gets up to speed? Now, let's take a look at this problem. And we're going to start by strategizing. Now, strategize in this case means this. We're going to describe how we are modeling the motion of the zebra. And let's take a look at the problem statement. We're told a stationary zebra accelerates at 4 meters per second squared until it reaches a constant speed of 11 meters per second. So it's a reasonable assumption that we can model this as motion with constant acceleration. And you're not told that, but it's a reasonable assumption. You're just given a single number. We can assume that that is a constant acceleration during that time interval. So that's our strategy. We're going to treat this as a problem of motion with constant acceleration. Now next, we're going to prepare, and the prepare step is the one that typically takes the most time. We're going to draw a visual overview showing important points of the motion, and then to that visual overview we're going to add data for the important points of the motion, and then finally we're going to collect together the equations that we can use to find the variables that we're looking for. So let's start, and I'm going to start like this. Okay, we start with a zebra at rest, and here's a zebra, and it looks a lot like my other African animals, and it starts at rest. So and then it speeds up, and sometime later the zebra is in motion, which I'm going to draw because the zebra is kind of like leaning forward here. Zebra is in motion, and it's moving at 11 meters per second. And between the first point and the second point, it accelerated with an acceleration of 4.0 meters per second squared. That's what my visual overview looks like, and you can see there's two important points of the motion. The first important point is zebra at rest, and right when it starts to accelerate. So it's at the instant it begins the acceleration, but it hasn't moved yet. And then finally, when it reaches its top speed. Those are important points of the motion because we're asked, how much time does it take the zebra to achieve its top speed? Oh, so that's from at rest to its top speed. And then we're also asked to compute how much time it takes, or how much distance the zebra covers as it gets up to speed. So it's how much distance as it covers from this first point, which we're going to label with the subscript I, initial, to the second point, which I'll label with the subscript F for final. And next, what we're going to do is I'm going to do values of the variables. And for the initial point of the motion, we can set the initial time as 0. That's when the problem starts. And we can choose that. We can choose any value we want, but just let's start the problem as t is equal to 0. That's the instant that the zebra begins to accelerate. I can set my initial position as being 0 as well. So 0 seconds, 0 meters, and my initial speed of the zebra is just 0 meters per second. So that's my initial situation. Now for the final time, I don't know. As a matter of fact, that's what I'm looking for. I'm looking for time. What's my final position I don't know. Again, that's what I'm looking for. How much distance does the zebra cover? But I do know the final speed, and the final speed is 11 meters per second. So this, what I've drawn right here, is my fully annotated visual overview. I've sketched out the motion, I've identified the important points of the motion, and said what are the values of the crucial variables at those important points of the motion. The next piece of the puzzle is I can gather together equations that I can use for solving. Now I'm given initial position, initial time, initial speed. I know the final speed. I'm looking for the final position and the final time. It's motion with constant acceleration, so I can look up relationships for motion with constant acceleration. And for the time, I can just say this. The final speed is equal to the initial speed plus the acceleration times the time interval. Well, the time interval is just the distance between the initial and the final time, and that's just equal to the final time because the initial time is 0. So I can take that equation, I can solve it for my time interval. For the position, my final position is equal to my initial position plus my initial velocity times the time interval, which now I know, plus 1/2 times the acceleration times the time interval squared. So next step, we can solve. And solving, we just do this. We use what we've done to compute the time and the distance for the zebra's sprint. But I want you to think about this. We've done a lot of work to get here. And by the time we're there, all we have to do is take the equations that we specified and put in numbers. And now I'm at the point where I'm actually going to solve the problem. And the way I'll do it is I usually actually rewrite the equation. VF is equal to VI plus the acceleration times the time interval. And I'll just write down what I know for each of the values. Well, I know that the final velocity is 11 meters per second. The initial velocity is 0 meters per second. The acceleration is 4 meters per second squared. And the time interval, that's what I'm looking for. And if I do that and I calculate the final value for the value for the time interval, I get the time interval is 2.75 seconds. But since this is a 2 significant figure problem, I have to round it to 2 significant figures. And the convention is, since the 7 is odd, I round up and I get 2.8 seconds. So my final answer is going to be 2.8 seconds. And to make it clear that I've rounded, I might put a little squiggle over my equal sign and say it's approximately equal to, then it's clear that I've done some rounding. Now the second relationship that we wrote was this. We wrote the final position, xf, is equal to the initial position plus the initial velocity times the time interval plus 1/2 times the acceleration times the time interval squared. And we know values for this equation, so let's go ahead and mark what we know. The initial position was 0 meters. The initial velocity was 0 meters per second. Oh, so this whole term drops out, which is handy. The acceleration is 4 meters per second squared, and the time interval, I'm going to use the 2.75 seconds because that's the most accurate value. I don't report that as my final answer, but I will use it in my calculation. And if I use those numbers and calculate my value for the final position, I get 15.1 meters, which of course I will round to 15 meters. And so the final results are, for the time, 2.8 seconds, and for the distance, 15 meters. Okay? Now the final piece of the puzzle is to assess your results and see if your results make sense. And there's 2 different ways that we're going to do this. And the first thing, I just want to do an assessment and say, does it make sense in terms of the world? So remember our answers. We said 2.8 seconds, and we said 15 meters. And just to see if it makes sense in terms of the way the world works, I like to change things by a factor of 10. Say, suppose I made it 10 times bigger or 10 times smaller. Would it make sense? So suppose I'm talking about a zebra getting up to speed. And instead of 2.8 seconds, suppose it was 0.28 seconds. Well, that's not much longer than the time it takes to blink your eye. Zebras can't go from 0 to 25 miles per hour in an eye blink, so that doesn't make any sense. Suppose it was 28 seconds. So the zebra goes from 0 to 25 miles per hour in 28 seconds. Well, if it takes you 28 seconds to get up to the speed that people drive around your neighborhood, you're not going to be escaping any lions. So that doesn't make any sense. We expect a number in the middle, so my suggestion is this number makes sense. How about the 15 meters? So suppose during its motion, the zebra only went 1.5 meters. 1.5 meters is like 2 small strides for me. So that's kind of ridiculous. When I take a stride, I take just shy of a meter. So that's like 2 strides, boom, boom. And the zebra is at 25 miles per hour. That's your super zebra. That does not make sense. On the other hand, if it was 150 meters, oh my gosh, that's a football field and a half. Zebra that takes that much distance to get up to speed, it's not escaping any lions. And so none of those numbers don't make sense. We expect the number to be in the middle, and so our 15-meter number seems reasonable. Now, the other thing that you could do, and I want you to think about this, is we could take the data and just do some seat of the pants estimates. Now, the acceleration is given as 4 meters per second squared. 4 meters per second squared, okay, remember what that means. That's equal to 4.0 meters per second. So that means the speed of the zebra would go from 0 to 4 meters per second in 1 second, to 8 meters per second in 2 seconds, to 12 meters per second in 3 seconds. So a zebra should get up to something just shy of 12. If the zebra has to get up to a speed just shy of 12 meters per second, it's got to get up to 11 meters per second. It should take it just shy of 3 seconds, which is in fact exactly what we found. And so again, our result makes sense. And how much distance will it cover as it gets up to that speed? Well, think about this. The zebra starts at 0 meters per second, finishes at 11 meters per second. Its average speed, therefore, is 5.5 meters per second. It's just the average of those two numbers. And if a zebra is running at 5.5 meters per second for 2.8 seconds, it's running about 5 meters per second. For about 3 seconds, I predict a distance of about 15 meters. And in fact, that is exactly what we found. And so again, we can see that our results make sense. So both of those ways are valid ways to assess your result. And you might do both. You might do both and tell us what you're doing so we can assess your process. Now, I want to make a point about the homework. You are going to take a lot of time on the homework. This is going to take you lots of time to complete these. And don't worry about that. This is time well spent. The time you spend doing homework is the time you spend developing your problem-solving skills. This is how you learn to do physics, is by doing physics. So take the time to do it. Take the time to sketch out what you're doing so we can critique your results. This is how you learn. Now the next topic which we're going to treat is something called free fall, and Milo is in free fall. And you would say, well, he doesn't look like he's falling, he looks like he's leaping. True dat, but he is in the air, and when you're in the air, the only force that's acting on you is the force of gravity, and when the force of gravity is the only force acting on you, that's what we call free fall. And I'll talk about that in the next set of slides.